All right. Can you hear me?
Yes, sir. Yes, sir.
All right, great. Sorry, I'm 4 minutes late. Also, I just wanted to apologize. I'm sorry about yesterday. Was that yesterday or the day before yesterday? We cut our class short because I had to attend to some agent work related issue. I do apologize for that. All right. So I guess we will start. Now I see Mr. Piwa here they're sharing. Are you sharing data or something? I don't know who that is. I don't know who Tapiwa is between the two of you actually, but that's good nonetheless. All right. So let me see if I can export this. Again, I'm sorry about what happened the other day. Very, very strange things happen sometimes, right? I think we're done. Okay. All right. So, but before we continue lecture series number 14, just a few things that I thought we'd chat about. Of course, just the usual. I want us to look at a high-level overview of how the performance was like in quiz number. Yes, we've regretted it, right? In quiz number 13. A bit impressive, right? But we know why. We know why it was a bit impressive, because you people probably use calculators, right? Now, I did mention last time, if you were using calculators, much better. This is much, much better. If you are using calculators, you want to make sure that between now and the time we start writing the exam, you understand these things, because these things are coming in the exam, right? You'll probably be able to get away with this during the upcoming test, class theory test number 2, but the examination is going to be done in such a manner that you shall not be able to do this, right? You'll be expected to show a waking, right? It's difficult, not really difficult. Actually, we can make it such that we can make the class theory test number 2 such that you show your waking. But I'm just saying, we know why this is the case, right? I don't know if what you did qualifies as cheating, but nonetheless, this is much, much better, right? At least we have about 75% of the class passing. Now, if you are amongst these 16 people, right, that failed quiz number 13, you need to up your game here, right? You need to up your game because it's clear that you don't understand what's going on. For me, right, I mean, you failing to use your calculator, right? You failing to use your calculator. You come here and you say 2020, convert this to binary. If you are failing to do this, or it's in hexadecimal, convert this to binary. If you're failing to do this, then there's something wrong with you. And we know what's wrong with you. You are not studying, or perhaps you're not really following through with some of the things we're discussing in class, right? Which is a bit unfortunate here, right? If you are failing to multiply, right? 2020 times 4, right? Because the other hexadecimal digit was 4. If you are failing to come here and say this times 100, right? What is the answer? Then there's something wrong with you, because this is something that you do within seconds. And in fact, we can see from the logs that the vast majority of you were finishing quiz number 13 in record time, right? Less than 15 minutes, actually. There's quite a huge chunk of you that finished the test in like between 10 and 15 minutes. We know why, right? So probably using online calculators and whatever calculators you're using, that's fine. But you better figure out how this thing works. All right. Then again, this is fictitious. You notice that at least normally this bar here, right, this long bar here, if you've been following through with what's been happening, is normally been associated with the lower grades, right? So the D pluses and the Ds. I'm going to double back here to showcase to you quiz number. Yeah, you remember this? You notice that it shifted to the bottom here. I don't know if it was the Lord, right? It was a miracle or something. I don't think so. Calculators, but at least this is much better than before, right? And the distribution still, even though it's not your normal bell curve, but at least we have a huge chunk of you that are scattered to the right, which is a good thing. All right, and then there were a lot of you got, I mean, 8 out of 10, and I think most of you lost marks for that question where we required that you You tell us what the carry bits were. Now, you telling us what the carry bits were involved you working out the solution, right? No calculator can show you how to do that. I mean, probably you'll be able to find something online, but you needed to show you're working. For us, this is a sign that people clearly were relying on calculators here, which is fine. Anyways, that's fine. Now, I want to say we tentatively, I had no idea that Sunday was a holy, apparently prayer day, whatever that means. But I wanted to mention that we tentatively have class on Saturday. Now, I'm saying tentatively because I'm not certain as to whether I will be available on Saturday, but I'll be able to confirm either on Friday or on Saturday morning or something. And then we have 2 quizzes next week, right? Because the plan here between Friday and Saturday, we should be able to finish off data encoding, or at least portions of data encoding, which stage we can pretty much write, we can write a quiz, right? So we have 2 quizzes, and the reason we're squeezing in these quizzes, we'll get to the slide just now. The reason we're squeezing in these quizzes is because we're only remaining with about, is it 3 weeks or something? Last day of class is, I think, the 6th or something of November, right? So I want to make sure that we are reaching here, but I was hoping we could squeeze in all the remaining 6 quizzes so that we have a total of 20. Doesn't matter if we write less than that because we're getting the weighted average nonetheless, right? So, but 2 quizzes, one on Tuesday and one on Friday. And then because Saturday happens to be a holiday again, we will not have a class, but we will tentatively have class on Sunday, right? So we won't have class on Saturday that week. Anyway, and so this is what I was talking about here. If you look at the calendar, you'll notice that we're only remaining with 3 weeks really, right? And unfortunately, I had hoped that we'd be able to cover everything that needs to be covered in 11:10, but that will not be possible. Now, for some of the topics so like the topics to do with MIPS assembler, for instance, the plan is for us to just gloss over them. So we generally spend anywhere between a month and maybe a month and 2 weeks or something looking at MIPS assembler. But because of the limited time that we have access to, we'll just skim through this topic. It's not really that crucial, right? So we'll cut it down so that we just spend maybe just a few lectures on it, right? Yeah, but between now and the 6th, the plan is to just do as much as we can here, right? And I think I forgot to mention something, but I just sent out an email. We have a test on the last day of class. I'm not sure how many of you managed to check your emails. Sent it a few minutes ago. But we have a test. I'm wondering why I didn't include this here. We have a test on the 6th of November, right, which is a Friday, obviously. So brace yourselves. You want to prepare for this. The content that's going to be covered is going to be everything covered in the course, excluding content that appeared in class theory test number 1, right? So I'm wondering why I didn't include that. Wow. Right. So I don't know if people have any specific concerns or questions or something to do with what I just spoke about here. If you still have queries to do with the grading of quiz number 13, just reach out to me privately, and then we can sort this out. But my understanding is that we've managed to iron things out, I think.
Sir.
Yes.
So we're going to write the second test minus having the first one and the quiz 3 and 2 graded.
Probably they're mutually exclusive. They're not linked in any way.
Oh, right.
Unfortunately, yeah. But hopefully, I mean, you should be able to finish marking before you write the test. But the way this works is that you don't write the exam without knowing your CA. But so whatever happens, you will know. You will have the results ready before you write the exam, essentially, for the assessment. All right, so we continue our discussion of lecture series number 14, right? And hopefully we can wrap up today, I guess, if possible. All right, so we've discussed, we're still discussing this whole notion of signed integers, and we've looked at 2 of the 3 techniques that we're supposed to focus on. So we looked at sign magnitude and one's complement. And now is the time to look at so-called two's complement, right? And I would like to draw attention, as we're talking about two's complement, I would like to draw attention to some of the shortcomings associated with sign magnitude and one's complement, specifically things to do with you having things like 2 different types of zeros, one with a positive sign, one with a negative sign. The fact that when you use techniques such as sign magnitude, for instance, you tend to work with significantly lower numbers, right? Because one of the bits is used as a sign bit, the remaining bits that are used for the magnitude of the number itself are significantly lower, right? Resulting in a fewer number of integers that you'll be able to work with, right? Something else I'd want you to think about as we're discussing two's complement is the issue to do with subtraction, right? And this mostly applies to sign magnitude. The fact that when you perform subtraction using sign magnitude, you typically end up with results that don't normally make logical sense, right? So classic examples we looked at is adding +1 and -1, or adding +5 and -5, for instance. You tend not to get what you expect, which is a 0, right? So this is what we're doing. This is where two's complement comes in, right? So the idea is to avoid having a situation where you have a +0 and a -0. So again, the leftmost bit is used to represent the sign, right? Same as one's complement, the positive number remains unchanged. When you're converting a decimal number into a binary number using two's complement, when you want to encode it using two's complement, if you're dealing with a positive number, the positive number will remain unchanged. You derive the negative numbers by flipping the bits and then incrementing by 1, right? Some interesting things here that you notice, like if you are to compare one's complement and two's complement, is that with two's complement, when you're dealing with carry bits, what you realize once you start going through the heuristics and examples is that we discard the carry bit, right? So in instances where you're subtracting, for instance, instead of adding it back to the least significant bit, right, the bit on the right side of the number you're working with, you discard it. It will make sense once we look at examples just now. All right, so more rules, right? It's about rules here, right? So to find the two's complement equivalent of a decimal number, given a decimal number whether positive or negative, you follow a very simple heuristic. You first of all check if the number is positive or negative. If the number is positive, then you directly convert the number to binary, right? To derive, and this is supposed to be to derive two's complement value, right? So you don't do anything, you just convert it direct from decimal to binary if it's a positive number. On the other hand, if the number is negative, right, what you do is you get the one's complement of the number, and then you add 1. Now you notice here, right, for the step number 2 here, or part 2 of our heuristic here, where you're dealing with a negative number, we kind of like omitted certain steps because we are fusing in a step associated with one's complement. Another way of looking at what we're doing as part of number 2 here, I hope people are able to put 2 and 2 together here, is that if you want to do it from scratch here, what we're saying here is that when you have a negative number, what you do is you convert to binary the positive equivalent of the negative number, and then you flip the bits, right? So this is this step here. Essentially what we're saying is that for you to get to a two's complement equivalent of a decimal number, you apply one's complement and then you add 1, right? So this is why we're saying we get the one's complement of the number and then we add 1. right? So you're adding 1 to the number, and then when you're adding 1, same binary addition rules will apply here, right? So in instances where you're adding some strange number, where you have this would be a very strange number, I guess, where you have a 1's complement equivalent number of 1, 1, 1, 1, and you add 1, right? Binary rules apply. 1 and 1 is 0, carry 1. 1 and 1 is 0, carry 1, and then cascade. All right, so here's just a few examples here. Let's look at some examples here. So if we're, yes.
I didn't really get the concept of one complement and how it works because of the last missed class says.
But the last missed class had nothing to do with 1's complement.
No, the last 2 missed classes.
What about the last 2 missed classes?
You said you were going to explain it better in the next class, which was supposed to be on Sunday. Then you didn't show on Sunday. Then you had to cancel on Monday. Then here today.
Did we not go through this example of 1's complement? Or did we not go through examples of 1's complement? Which part of 1's complement is not making sense for you?
Just the whole thing, sir, to be honest.
Well, I'm going to pause here. Is there anybody else who is not clear with 1's complement? A discussion that we had about 1's complement. Is there who was able to understand what 1's complement is all about out of the 27 of you that are in the room right now?
The way I understood it, when you have been given, let's say 4, then you have to convert it in decimal. Then you flip where there are zeros and 1 to where there is 1 to become 0. That's what about 1's complement.
Yeah, I mean, I can't quite remember what I said I was going to do here, but the rules are simple here, right? And here's the thing. I'm going to ask whoever is not interested. It's a good thing we're recording these sessions, right? Go and play back the lecture series where we went through the rules, right? It's just the rules here. Simple rules. This is what we're doing. I'm going to pause anyway. I won't proceed. I'm going to pause. Which part of this rule here, when you're converting a number to 1's complement, which part of this rule is not clear to you? Out of these 2 rules that we have, when we're saying if we have a positive number, sorry, this rule is here. When we have a positive number, we just convert it direct to binary. If you have a negative number, you convert the positive equivalent to binary, and then you flip the bits. Which part of the rule is confusing, or which part exactly is confusing to you? I want to make sure that we're on the same page. You want to be very clear about which part is not very clear to you.
Yes, just flipping the bits, that's all.
Yeah, but flipping the bits is what part about flipping the bits is confusing? If you have the 1, turn it into a 0. If you have the 0, convert it into a 1. I mean, if you have a number like this, what we're saying is when you're flipping the bits, all you're doing is you get the opposite of what you have. The opposite of 1 is 0, the opposite of 0 is 1. Flipping the bits simply means you get the opposite. Opposite of 1 is 0, opposite of 1 is 0, opposite of 0, 1, opposite of 1, 0. This is what we mean by flipping the bits.
That's all.
That is all, which is why I'm confused here when you're saying it wasn't clear.
Okay.
But I would appreciate it if you told us what exactly you're struggling with.
All right, sir. That's all.
Yeah, because going back through the whole thing just doesn't make sense, right? These things are recorded. I do encourage you to, because what I was just talking about just now is somewhere in one of the archived video footage, right? So I do encourage you to play back the segment where we're discussing these things. Simple, right? And then the other part is just doing the opposite, right? When you're converting, when you want to derive a decimal number from a 1's complement encoded binary number, again, it's just the rules, right? If you have a 0 as the leftmost bit, then you know that you're dealing with a positive number. And so what you do is you just directly convert that decimal number into, that binary number into decimal. If you have a 1 on the most significant bit, or as the most significant bit, or the leftmost bit, then you know it's a negative number. If it's a negative number, what you do is you flip the bits, you convert the resulting number into decimal, and then you place a negative sign. So, don't know here. I mean, we went through these examples as well, where you have 0, 1, 0, 1. We know that this is a positive number because of the 0 on the most significant bit, or the leftmost bit, right? So what you do, you just directly convert it, right? If you have a number like this, where you have a 1 on the most significant bit, or the leftmost bit, then you know that you're dealing with a negative number. So what do? You go through this heuristic where you flip the bits first, get the opposite of 0, get opposite of 1, you flip the bits, and then you convert the resulting number here into decimal. Then you place a negative sign because the 1 here on the most significant bit signals the fact that you're dealing with a negative number. These things, right? These things to do with rules, and we're dealing with very trivial rules here. These are not complex rules. You only get to start dealing with complex rules, I guess, in courses like 2010 or something. Nothing complex, actually. But anyway, I do encourage you to do that. I mean, then the other thing here is this idea of when you're dealing with subtraction, which we went through as examples. All right. So anyway, so this is what we're saying here with the rule associated with 2's complement, to say when you have a positive number, you derive the decimal equivalent the same way you derive 1's complement, right? Because all you're doing is just converting the decimal number into binary without doing anything. If you're dealing with a negative number, on the other hand, what you have to do is you get the 1's complement equivalent of the negative number, and we know what that means. You first of all get the binary equivalent of the positive variation of the negative number, and then you complement them, you flip the bits, right? After flipping the bits, what you're getting back is 1's complement, and then you add 1 as the last step, right? And the adding of the 1 here is, I guess, the part that might be a bit confusing, but fear not. I do believe that once we go through a few examples, this should make sense here, right? I will start with a simple case of -5. I'm quite sure why we're dealing with -5 here. To apologize, can I just close the window? Noise. I don't know if you can still hear me. Someone was trying to.
Yes, sir, we can.
Okay,
Yes, sir.
thank you. Beautiful. Right. So let's say we want to convert -5, right? -5. Very, very trivial process. We are saying for us to get the rules, but for us to get here, maybe we can use this, and then we use the spreadsheet once we look at the different example. You have -5, right? Base 10, and you want to convert it to binary using 2's complement. You have 2 rules that you're working with. If it's a positive number, then you convert it direct from decimal to binary. If it's a negative number, though, what we need to do is we need to get the 1's complement equivalent of +5. So what do? We first of all flip the bits, which is this step here, right? We flip the bits. After we flip the bits, we get the 1's complement equivalent of -5, and then we add 1. Adding 1 is easy here. We're adding 1 to the 1's complement derived here, right? So 0 and 1 is 1, 1 and nothing is 1, 0 and nothing. Right? And so this would be the 2's complement equivalent of -5. Now you can already notice here that, I don't know if you can notice a pattern here. You can already notice that there's some variation here in the encoding, right, of these binary digits. When you compare 1's complement, which is what I've just highlighted here, with 2's complement, right? The bits are different. The only semblance here is the negative sign, which is the 1, and we did mention that the last bit still signals whether it's a positive number or a negative number. Yes, sir.
So you're saying if it's a negative number, then we flip it and we add a 1. Since it's -5, and we suppose when we flip it to be +5, then we add a 1.
Sorry?
You said if it's a negative number, you flip
Yes.
it, then you add a 1.
Yes.
Now, it's saying convert -5. So when we flip it, it's going to be +5. So when we add 1 to +5,
No.
is 0, carry 1, then another 1 here.
Yeah, no. When you're confusing yourself here. If you look at what we're flipping is not -5. What we're flipping is +5. What you flip is a positive number. Observe, follow through here, right? Let's do this stepwise. Right? We're working with +5, yeah.
Didn't you say we flip the negative numbers instead of the positive ones?
No. Okay, let's do this together. Well, no. Yeah, clear. Okay, that's fine. Let's clear. We didn't follow through with one's complement, then everyone was right? Here's the thing: when you have a negative number like -5, when you want to convert -5 into one's complement, what do we do? Oh, also, guys, one's complement sometimes is represented as like so. Yay. Okay, what do we do? One's complement. What are the rules? Okay, I'll do it. Since I've been doing this for a very long time, so I'll do it anyway. Step 1, right? For one's complement, we're saying step number 1. We get, if you're converting -5 to binary using one's complement, you get binary equivalent of positive value. What we mean here is that when you have a -5, when you're converting one's complement, as a first step, you get the binary equivalent of 5. Yes, you're converting -5, but you get the binary equivalent of 5, +5. Bearing in mind that the most significant bit, which is the leftmost bit, must be a 0. What is 5? 5, you're adding 1's place and 4's place, right? So you're adding 1's place and 4's place to get 5. So what we're saying here is that our 5 is this. Agreed? Is this
Yes,
5?
sir.
Yes, sir.
Yes, sir.
Yes. Step number 2, we are saying flip the bits. Right? What is the opposite of 1? 0. Opposite of 0, 1. Opposite of 1, 0. Opposite of 0, 1. But we have here, highlighted in yellow, it's a yellow king now from True Detective. This is the one's complement, equivalent of -5. Do you understand? First of all, you get the binary equivalent of the positive equivalent of the number you're converting, which is this. And then you flip the bits. For 2's complement, what we are saying is step 1, get 1's complement of negative value. Now, when we're saying get 1's complement of the negative value, all we're saying is follow through with these 2 rules here. As a first step, get the 1's complement encoded binary value of the negative number you're evaluating. So we go through these steps. So you can look at these as being sub-steps of step number 1 for 2's complement, where you get the binary equivalent of the positive value, right? That is the same as this negative value. And then you flip the bits. After you flip the bits, now here we already have the answer, which is 1, 0, 1, 0. Step number 2, add 1 to the 1's complement value, right? All we are going to do here is we're going to say we are going to add 1 here. Come on, add 1. And then when you're adding 1 here, it's what, 0 and 1 is 1. 1 and nothing is like 1 and 0, which is 1. 0 and nothing is 0. 1 and nothing is 1. And then we find this answer here. So when we're saying we are flipping the bits, we're not flipping the negative value, we're flipping the positive value, because as a starting point, when you're dealing with one's complement, you first of all get the binary encoded value of the positive number that is equivalent to the negative number you want to convert. Is this making sense?
Yes, sir.
Is there anyone who's still unclear about what we're doing?
Yes. So can I just ask for your clarification? So for example, if you are dealing with -7,
yes,
so
beautiful.
you first turn it into a positive, then that's when you can get the one's complement.
Yes. So what you do is with -7, as a first step, you say get binary equivalent of 7. Yes, you know you're dealing with -7, but you get the binary equivalent of 7 or of +7, right? As you normally would, or convert 7 to binary, not -7, but 7 to binary, right? In which case you know that it's a 6 plus 1, right? So it's going to be 6 plus 1. 1's place, we need 2's place, we need this place as well. Yeah? So we have 4 plus 2 plus 1, which is 7. Now remember, when you're converting, when you're dealing with 1's complement or 2's complement, you must remember, right, that the most significant bit, or the bit that is on the leftmost side, must signal the sign of the number. So if you're getting the binary equivalent of 7, you know that the leftmost bit here, after you get the magnitude, which is 7 here, this must be a 0 to signal the fact that you're dealing with, this is a positive number. And then step number 2, flip the bits. 1 is 0, 1 is 0, 1 is 0, 0 is 1. So this would be like this would be like 1's complement, right? 1's complement. I guess just put it here, I suppose. 1's complement. And then for 2's complement, all you're doing is, for this, because you go through the same step where the step 1 is you convert the negative number to 1's complement equivalent, right? And then afterwards you add a 1. So essentially what we're saying is you go through step 1 and step 2, and then as a third step, you're going to add 1 here, right? So you're essentially just going to have 1, 0, 0, 0 plus 1. That's it. It will be 1, 0, 0, 1. Is this making sense?
Yes, thank you, sir.
Yes, sir.
All right. Great. So we have an example here of
Sir,
yes.
I have a question. How can we evaluate two numbers? Let's say -21 base 10 plus 6 base 10.
Negative?
-21 base 10 plus 6 base 10.
Well, I mean, so it depends, right? Normally, if you're asked such a question, or if someone approaches you and you need to do this, they'll tell you what method you need to use, right? If they don't tell you, then you get to choose which method you want to use, right? So you can either evaluate these using...
I mean,
sorry?
Using two complements.
Yeah, we're getting there. We haven't gotten there where we... Sorry, there are rules. There are more rules for subtraction. We'll get there. Just pause, hold your horse, and then we'll be able to discuss this if this is what you're asking. Let's check here. I hope there is an example here. There we go. So we'll discuss this, right? And this is where the part where I was saying when you have a carry bit, the only difference, if you have to compare 2's complement when dealing with subtraction, is you discard the bit for... You discard the bit for 2's complement, but for 1's complement, you add the bit, right, on the other side. So we'll discuss it. But anyway, so we were to, now I want to draw attention to that table that we're looking at where we had negative numbers and positive numbers, right? If we're to redraw that table here and we take into account the heuristic that we use to derive negative values for two's complement, what you will notice is that we end up with this sort of scenario, right? So I want you at your own time, just go to slide number 360 and try and see if you can convert these numbers here, the positive numbers to negative numbers, 0 through to 7, right? Using two's complement. You should be able to get what we have here, yes? Now what we're saying here is that already, right? Already, once we add the 1 here, this is 1's complement, we want to add the 1 here. What you will notice is that the problem we're grappling with, the fact that we had a scenario where you had negative 0 and positive 0 being encoded using different B patterns. You notice that this problem goes away once we use two's complement. So this is 1's complement. When we add 1s to these numbers, these negative 1s, there's the last step here, add 1, we end up with this sort of scenario. And this is what we're interested in, right? A situation where negative 0 will still be 0, 0, 0, 0. Positive 0 is 0, 0, 0, 0. So we have 1 representation for negative and a 0, right? Whether it's positive or negative. Now we know there's no negative 0, positive 0, but people make things up. We can make things up ourselves anyway, right? So that thing is gone now. Yes.
Yes, is there a difference between the positive 1's complement numbers and 2's complement positive numbers?
Sorry?
Is there a difference between 1's complement positive numbers and 2's complement?
No, they're the same because the heuristic we're using is the same, right? We're saying if you've been following through with the rules, right? If you remember what we discussed in 1's complement, what we said was that when you're converting a number, a decimal number to its equivalent 1's complement, if it's a positive number, observe. If you're dealing with a positive number, observe this here. If the number is positive, we're dealing with 1's complement now, convert the number to its binary equivalent. Just convert it to binary. That's it. This is 1's complement, yeah? For positive numbers. If you look at what we're doing in two's complement, we are saying again, if you follow this heuristic here, if the number is a positive number, all you do is you just convert the number to its binary equivalent. This is two's complement. So there's no difference, the same. Here's a question for you. Is there a difference between a positive number encoded in same magnitude and a positive number encoded in 1's complement and 2's complement? I don't know, right? Think about this before you sleep today. So I hope this makes sense, right? The fact that things are pretty much making sense here. There's a thing here, right? Some other interesting things that you can kind of try out here is using this table here, 0 through 7, negative 7 through to positive 7. What you can do is you can start playing around with these positive numbers and negative numbers and see. Ask yourself, if I have a 7, which is, if I can just do this now. Just do this. If I have a 7, right, which is, wow, which is 0, 1, 1, 1. Yeah. If I have this number here, 7, if I know that this is positive 7 and I try and add negative 7, which is 1, 0, 0, 1, 1, 0, 0, 1, what do I get? These are the things you should be thinking about as you're going through these notes, right? What do I get when I add these numbers? What we're saying is when we add positive 7 and negative 7, we must get a 0, right? This is positive 7, this is negative 7. 1 and 1, 0. 1 and 1, 0. Carry 1. 1 and 0 and 1, it's 0. Carry 1. 1, 0, 1, it's 0. Carry 1. 0, 1, 1 is 0. Carry 1. Right? Now I know what you're thinking. Well, but Lighton, the carry bit here, two's complement. One of the rules when you're subtracting is when you have a carry bit, an overflow, discard it, throw it away. And what you have here is 0. You understand this? Then, in fact, if you play around with all of these numbers here, if you add 11110 and 0010, you will get 0. If you add any negative two's complement encoded binary number with its equivalent positive binary number, what you realize is that you will get 0, which is what we want. Which is what we want. It works, right? Okay. I hope this makes sense here. It does to me anyway. But so here's the other way. Here's a different question, different way of looking at what we're doing here. If we can convert a decimal number to two's complement, question is, can we convert a two's complement encoded number like 0111? If we're told this is encoded using two's complement, can we do the reverse? Can we derive a decimal number? Well, we can. There are rules, right? All we have to do is follow the rules. So if you're given a two's complement encoded binary number and you're told to convert it to decimal, you follow the rules, right? First step, or rule number 1 is, if the leftmost bit is a 0, you know this is a positive number, right? What you do is you just convert the binary number directly into decimal using repeated multiplication or whatever fancy method you've invented, right? You're smart people, I'm sure you've invented methods. But the key thing is you just convert from binary to decimal directly, yeah? If on the other hand, what you're dealing with is a binary encoded number which has a 1 on the most significant bit, or if there is a 1 on the leftmost bit. The leftmost bit is always the most significant bit, right? What you do is you go through these steps. You first of all flip the bits, then you add 1, and then you convert the resulting number into decimal, as you would normally, right? Repeated multiplication. And then as the last step, you place a negative sign, bearing in mind that the most significant bit on the two's complement encoded number was a 1, meaning that it's a negative number, so you must place a negative sign. Very simple rules, right? Again, flip the bits, add 1, convert to decimal, place a negative sign, and then you're done, right? And if you think about this, right? I'll pause here and think about this for a second. You realize that all we're doing is we're just flipping, we're just doing the reverse of what we are saying we do here when you have a decimal and you convert into two's complement. Oh, I'll get the number and get to 1's complement equivalent and then add 1, right? So I hope this makes sense. Let's look at some examples here. Maybe it will make sense. Observe. You're given this number, right? 1010, right? Now I know what you're thinking. Well, we know what that number is, Lighton, right? 1's place, 2's place, 4's place, 8's place. So it's 10. No, it's not 10. If this was encoded using just normal binary, it would be 10. But because we're dealing with two's complement, we must follow the rules. The previous rules we discussed do not hold, right? I know, but when you're using sign magnitude, you realize that this would be different because all you do is you assume this is a negative sign and then you get the magnitude. This is like -2. But because we've been told that this number here, 1010 base 2, is encoded in two's complement, we must follow the rules. Simple rules. As a first step, flip the bits power, right? 0 is 1, 1 is 0, 0 is 1, 1 is 0. Right, so we flip the bits here. As a second step, add 1 to what you get here as a result after flipping the bits. So we add 1, right? What do we get? 1 and 1 is 0, remainder 1, 0 and 1 is 1, 1 and nothing is 1, 0 and nothing is 0. And then we convert this resulting number here, 0110, into decimal, normally, right? Repeated multiplication. So 2's place, 1's place, 2's place, 4's place, 8's place. So it would be 4 plus 2, which is 6. And then we place a negative sign. Yes, sir.
Why is it that we keep on adding? Because I remember even when you're converting, you have to add. Why don't you, at a certain point, subtract?
Well, because ideally, if you think about it, addition is more or less a subtraction problem can be viewed as addition. Think about this for a second. That's a nice way of what's a nice way of thinking about this? Do you realize that when we get to a stage where we are flipping the bits, essentially we are doing what we said we're doing, we're getting the opposite of the number we had. So it's like Anyway, a simple answer to that question is a subtraction problem can be viewed as an addition problem. Here's the thing. What I want you to do, right, tonight before you sleep, and I hope you'll be able to do this, try and subtract and try and see what you will get, right? What I do suspect you could do is maybe try and see if before flipping the bits, you can subtract and try and see if you can get the same resulting value here, right? So response to your question is, when we flip the bits, it's like we're getting the opposite number here, we're complementing it, so we have to add one, right? It's like we're just subtracting, essentially. A simple response to you, I guess this is what I should have started with. We are doing this because it's part of the rules. This is the only way it works. Are there any other questions?
So, and we essentially just changing signs before when we tried before flipping. If the number is a negative sign, it has a negative, you turn it to a positive, and if it's positive, you turn it to a negative.
No, we're not changing a sign. If you were just changing a sign, you'd be working with the most significant bit. Remember what we're saying, you know, these different instances, sign magnitude, one's complement and two's complement. The leftmost bit tells you what sign it is. So if you are changing the sign, all you do is you just change the leftmost bit. This is not what we're doing here. We are flipping all the values. Right? That's what I'm thinking.
That's the reason why we are flipping it.
What do you mean? That's a reason we're flipping it. What's the question?
Like the first number there, 1010. The most significant bit is 1, which makes it a negative, right?
Yes.
And then if we flip it, it becomes a positive, right?
Well, I don't want to say it becomes, yeah, I guess one way of looking at it is it becomes a positive number, implicitly, anyway, because essentially if someone tells you that this is an intermediate step, but you're working with two's complement, the moment you see a zero on the leftmost bit, then you know you're dealing with a positive number. So yes.
All right, sir. That's all. That's fine.
Okay. All right. What you want to do is just play around with, and there are plenty of tables here. What I want you to do is just play around with these different tables and then try and see if you can get to so you come to the hits, can you get to from negative 1011? Can you convert this to decimal? Can you get -5, right? By following the steps we're looking at here. Okay. So this is I don't know if it was Slesho was asking or Anita or something. I can't tell the voices apart here, but there's a question. But if we're given such a scenario here, I mean, how do we evaluate this using two's complement, right? Well, the answer is coming here. More rules, right? More rules coming our way, which is the rules here. There we go. So for you to subtract two numbers using two's complement, what you do is, as a first step, you get the two's complement equivalent of the numbers you're working with, and then you just add the two numbers. When you add them in an instance or a situation where you have an overflow, a carry bit, you discard the carry bit. Now, this notion or idea of an overflow of the carry bit comes up in a situation where, let's say you're working with 8-bit encoded numbers. If your resulting value has 9 bits as a solution, you discard the overflow is as a result of the most significant bit, the additional bit that you have. So what we're saying with two's complement is you discard it. If you remember, in one's complement, we were adding the carry bit to the least significant bit, which is the rightmost bit. Do you remember that? What we're doing in this case for two's complement is we're saying you throw it away, discard it, take it away. And this is what I was showcasing to you here when we were looking at this example here. Do you remember this? When I was saying this was two's complement, we were adding this. After adding, what you'll notice here, just as well I've dropped the one here. We're working with 1, 2, 3, 4 bit representation. The answer is 1, 2, 3, 4, 5. Because the answer is 5, it has 5 bits. This is an overflow. This is what we're calling an overflow. You discard this. So your answer is this. With one's complement, though, the way we deal with an overflow is we add this to the least significant bit or the rightmost bit. Is this making sense?
Kindly go over that again.
Over the rules. The rules is you get 2's complement, and then you add the resulting binary numbers. When you're adding the numbers, if you get into a situation where you have an overflow, you discard the carry bit, throw it away.
Right, sir.
Discard the carry bit, throw it away, right? Observe, let's say we're dealing with this thing here. I don't remember what this number is, we'd have to convert it using 2's complement. But assuming we get into a stage where, I think I can, there's a table here now. What is this number? Is it 7 and -6? So this is beautiful. This is +7, this is -7, right? We've converted these into 2's complement. These are both 2's complement encoded numbers. We are applying binary subtraction using 2's complement. What do we do? Because this is negative positive. This can be viewed as a addition problem, right? Because we know this is negative, this is positive. We are adding a positive number to a negative number. So carry bit result. When you add 1 and 1, what do you get? You get a 0. Remainder 1. Jeez. When you add 1, 0, 1, what do you get? You get a 0. You carry 1. When you add 1, 0, 1, what do you get? 0. Remainder 1. When you add 0, 1, 1, what do you get? 0. Remainder 1. Carry bit. You're working with 4-bit representation. This carry bit here, if you add it here, you have 1, 2, 3, 4, 5. Discard this, throw it away. It's useless, right? So the answer is going to be 0, 0, 0. 0, 0, 0 is what? It's 0. And it makes sense, right? We are saying when you add +7 with -7, you must get a 0, which we have here.
Sir.
Yes, sir.
So if you are told to give, tell which ones, how many carry bits are there, do you have to add the one you discarded or just put them all, the 4 ones?
When you're told to do what?
To write down the carry bits.
Well, when you're told to write down the carry bits, and I know this is coming from the quiz session, you write these things here. These are the carry bits here. And that thing was there because I knew you were going to cheat, right? You were going to use calculators. And I know this, right? You use calculators. That's fine. You better learn how to do this though. That was trying to assess if you truly understand the process we're going through. And more of these are coming your way, right? Where you won't be able to use your calculator. You have to take out a pen and a plain piece of paper and work this thing out. So you better learn how to do this, especially for the upcoming quiz, right? So if you're told to tell us the carry bits, you just 1, 1, 1, 1. These are the carry bits here.
All right, sir.
Yeah, listen, this is almost 6. Pause here. I want you to think about this, and then on Friday we will
last question.
hopefully finish this off. Yeah, sure. On Friday we will finish this off. Oh, almost done. Right? On Friday we'll finish this off and then start lecture series number 15. So also what I want you to do is between now and Friday, remind me if I forget this, but there was a question that came through with regard to -26, and I want this to be homework, and then we can revisit it. People will be a bit confused. We can look at this. I want this to be homework. Someone asked a question, but I would like this to be homework. Follow the rules and evaluate this using 2's complement. Thanks for the question. Yes, what's the question?
Oh, it's fine. It was concerning the same example.
Which example is that?
The previous one. Let's say we are using 8-bit representation. How can you handle the same example which you have provided previously?
Well, you just pad zeros and then make sure that the leftmost significant bit is either a 1 or a 0, depending on whether you're dealing with a negative number or a positive number.
Okay.
Yeah. Good stuff. And it's unfortunate that we won't be able to play around with QtSpim, but you'll have seen these things in action using the simulator here, because it turns out that maybe we can sneak in a few things, just a few demos or something, I don't know. Very, very sad. COVID-19. See you on Friday. Thank you.
Sir.
Yes, sir.
Okay, it's not regarding what you've done tonight, but I'm unable to view my previous quiz course.
Okay. you want to reach out to me privately and then we'll sort this out? I remember you sent me an email, but I thought that was fixed or something. It must have been deregistered at some point, right?
Yes.
Yeah, that's probably the reason why. I mean, just reach out to me again. Just make sure you use the same email, and then I'll try and see if I can look into it. Last time you sent me an email, though, I did check, and the quiz, the historical record of the quiz is out there. So just reach out to me, and then I'll try and see if I can fix this.
Through the mailing list or your person or your.
No, it doesn't involve other people. So just send through to my person. Just send the email to me alone.
Right.
Yeah. Let's say like how many megabytes? I don't know what this is, or rather, can I watch 720p video on YouTube without lag? I don't know if this is directed to me or you're talking amongst yourselves. But you can if you have a stable connection, right? You can actually watch 1080p if you want to, but that's more money. I mean, if you have a lot of money, you can do that. That's fine, I guess. You can. Oh, we are discussing these things, by the way, in the lecture series. Please do attend this. We look at, if you start looking at video encoding, we look at these things. We look at compression also. I mean, granted, we just, it's just going to be a superficial discussion, but it's interesting nonetheless. Thank you. See you when you see me.
Oh, Dr. Layton, before you go.
Yes, sir.
Oh, with two's complement, it seems that it handles a lot of flows that came with one complement. Do you have any flows for two's complement, or it's actually the base that is actually being used? So we don't have like any flows.
Oh, I don't know. I mean,
complement.
Yeah, I don't know. I mean, so for now, I mean, most computers typically encode numbers using two's complement, right? So it's possible that flaws are there, right? And there are smart people that are constantly working on these things, and hopefully some smart people come out of your group and find themselves doing these things. But not that I know of. I don't know of any encoding scheme that's there that's more superior than two's complement. It's possible it's there, right? People are always doing crazy things. So the answer is I don't know. It'd be nice if you would look it up or something. Okay. So see you when you see me. Thank you.
Thank you, sir.
Quiz on Tuesday.
Wait.